Long, long ago, in a very near land, I had a grievance with the solution in the back of the textbook. Students insisted that I had steered them wrong. I did not. It's just that the textbook uses a particular convention that I was not using. So this video, after I have recently encountered those pictures again, serves two purposes. First of all, vindication. And second of all, here's how to do it the way the textbook expects you to, so that your answers will always match the back of the book. This is number 13 in the Stewart book. Now, I'm showing my work. It is correct, I promise. However, my answer doesn't match the back of the book. And students are insisting, but you're wrong about this. But it's not. It's not. And the student insisted, you have to do it with the secant. The student drew the orange triangle and moved the theta to a different spot than mine. So begrudgingly, I used the secant. And then my answer matched the back of the book. He said, see, it's correct now. I grumbled, it was correct before. More on this later. We're coming back. Let's start at the beginning. Who thought it was a good idea to introduce trigonometry when there was no trigonometry before? Well, you see this denominator has a square root in it? It's kind of gross. It's going to mess up my whole integral. How would I possibly solve this problem? But whenever you see something that looks Pythagoreanish, in other words, there's a square root and you're adding or subtracting some squared stuff, looks kind of like the Pythagorean Theorem, then we could introduce trigonometry to make it easier. So first of all, we're going to identify that there's a square root with the sum or a difference of squares that's making your integration kind of frustrating, like this one. Sometimes they're kind of hidden. You see that raised to the 3/2 power? The fact that it's 3/2 power means that you have a square root. Next, we're going to draw a right triangle, and that pesky radical is going to be one of the sides of your triangle. Make sure to label a theta because we're going to be switching variables. Now let's reason through the Pythagorean theorem. Your hypotenuse has to be the longest positive side, which means that our longest side has to be the square root of 25. That's the biggest one. So the square root of 25 is 5, and then that means your other leg is the square root of x squared, which is x. Here's the beautiful part. We're now going to build a ratio of the sides that don't have the annoying radical in them. We want to build something out that looks like x over a number, or variable over the number. So the obvious thing here would be an opposite over hypotenuse in reference to theta. Well, opposite over hypotenuse is sine. So the sine of theta equals x over 5. No radical in that. Then it's easy to solve for x by multiplying both sides by a constant. And I'm going to need a dx too, so we might as well take the derivative of both sides. Now we can substitute x and dx in terms of theta. Notice how I end up with the square root of 25 minus 25 sine squared theta. Well, that's just 25 times 1 minus sine squared theta, which is 25 times cosine squared. And that has a nice, beautiful square root. After we do all of the simplification, look how we don't have any square roots left. It's getting prettier, but wait, there's more. We keep on simplifying with these beautiful trigonometric relationships, and this whole thing simplifies down to the integral of tangent squared of theta d theta. That's so much nicer. Trigonometry made this so much easier for us. That is an integral that we have no problem with. The integral of that is tangent theta minus theta plus c. One problem. We're still in terms of theta. Let's use our triangle and back out of thetas and go back to x's. So whenever I see a tangent of theta, well, I need to go back to my triangle and use the opposite over the adjacent, which is x over the square root of 25 minus x squared. And whenever I see just a regular theta with no trig attached to it, well, we know how to use an arcsine. So that means that this whole nasty business ended up being x over the square root of 25 minus x squared minus the inverse sine of x over 5 plus c. Therefore, if you have a square root with a sum or difference inside of it, and it's making your integral very difficult, maybe a little Pythagorean theorem might help you out. let's get back to the real story, which is about me beefing with the back of the textbook. I would love to draw every triangle like this, which means that for this problem, then x over a constant would obviously be a cosecant. And so I did the whole problem with a cosecant. I mean, we're making up a triangle anyway. I can pick, can't I? The problem is that the text favors sine, tangent, and secant. And I mean, don't even get me started on, I don't even like their order. But without triangles, and I was originally taught to do this without triangles. It's just here, memorize these sequences. The nerve. And therefore I submit that my original answer was not wrong. It was just off by a constant, and you can't see the constant because the plus c ate it. Perfectly fine. In fact, the constant that the indefinite integral ate was a pi over 12. So if I add pi over 12, then they overlap. Had it been a definite integral, the answers would have come out the same anyway. But I concede that if we want the answers to match the back of the textbook, we're going to have to use sine, secant, and tangent, sometimes begrudgingly. Let us discuss how to build the right triangle every time. Pun. The most obvious one to identify is that the one with the plus sign has to be the hypotenuse, because in Pythagorean Theorem, it's the c squared that's equal to the sum of the other things. So you must set that one as your hypotenuse, and then you set your x to be the opposite of theta and your constant to be the adjacent of theta. Therefore, clearly, the one with the plus sign is going to be a tangent. The next is when you have the square root of a constant squared minus x squared. And then we're going to put the radical at the bottom, just by convention. Then your x and your a are going to be your opposite and your hypotenuse, and that's how you're going to build out a sine. So whenever you have a constant squared minus an x squared, that's a sine. The last one was the constant squared minus the x squared. This one switches the order, so it's x squared minus the constant squared. Now, if you're going to put your radical at the bottom of it, like I typically do, then if you're going to get a secant, you got to put the theta in the other spot. And that way your secant is going to be hypotenuse over adjacent. And if you want to keep your theta in the same spot, that's fine, but you're going to have to move the radical to the other leg, because you need x over a not to have any radicals in it, and you don't have the option of cosecant if you want to match the back of the book. So that's going to be your hypotenuse over adjacent again, but with no radicals in it here. And while I am absolutely not recommending that you memorize a chart, but instead see all the connections at one time so that you can build it from memory every single time because it just makes sense, here is a chart.